Hello everyone, welcome back to LeetCode Daily Live where I do the daily question raw and uncut. So we have a hard today called sum of k-mirror numbers. So let's read the question and see what it wants. So a k-mirror number is a positive integer without any leading zeros that reads the same both forward and backward in base 10 as well as in base k. Okay, let's look at this example. So for example, 9 is a 2-mirror number. The representation of 9 in base 10 and base 2 are, 9 and like 1001 respectively, which read the same both forward and backward. On the contrary, 4 is not a 2-mirror number. Because like 4 in base 2 is 100, and that's not a palindrome, right? So I think like mirror like basically just means palindrome. And like 9 is like one character, right? And obviously that's like also in like palindrome. So so that'll work. Okay, given a base k and a number n, return the sum of the n smallest k mirror numbers. Okay. So let's look at some examples. So if k is 2, n is 5, then we should look at how big they are first. Oh, k is only up to 9 and n is only 30. That's quite interesting. Okay. Yeah. So does it say like modulo though? Okay, it doesn't say modulo, so I'm assuming the numbers aren't that large. Okay, but let's just look at some examples. So, 5 smallest 2-mirror numbers, it'll be these ones. Right. So for base 10 we have nothing to worry about because like they are all how do I say it? They're all like one digit, right? So they're obviously mirror. But for like base 2, all these are mirror as well. So like we just add them up. This case is a bit more tricky, looks like, because we have like some larger numbers. So k is 3, n is 7. So the 7 smallest 3 mirror numbers are and their representations in base 3 are listed as follows. Yeah, so 1 and 2, that makes sense. And then we have 4 and 11. Yeah, so in base 3 this would be like 3 plus 1, right? And then you have like 6 and 2 here. So we'll have 8 here. But then like for these cases, like we see that both sides are palindrome, right? And like if you calculate this out, so like 1 plus 3 plus 9 plus 27 plus 81, I should give you 121 there. And then like you just want to like sum all of them up. Okay, and then like this one is even larger. We have like this here. So I think for this question I might just cheat a tiny bit and just see the largest number I can go to. So I'm guessing like 9, maybe that's like the largest. We can put like, I don't know, like an 8 and a 7 here. So I'm gonna cheat a tiny bit and just like look at the I need to do like return. Yeah, but I think like it doesn't go above. Yeah, so it doesn't go above like what, 4 billion for in 32s. What about these cases? Oh, this one is like even larger, right? Wait. Yeah, okay. So but it wants us to return it as an int. Yeah, this one is like enormous. Wait, does that mean like the lower it gets, the larger it could be? Yeah. Oops, I changed that. So let's do like 3 and then let's do like 2 here. Yeah, but when it says int here is not it's not in 32. Like look at how big this number is. Wait, this is like a million. Yeah, this is like 43 billion, right? So so obviously we can't just brute force our way. Seems like what is this? Like 1, 2, 3. So okay, so that's 2 billion. Okay, what about 6? Yeah, I'm just playing around with these enormous numbers. I'm trying to see what the upper bound is for this question. So that's 5, and then 6 is 6 is like smaller. I guess another way to cheat this question is to just generate all the answers. Like, cause like you only have like what, like 8 of these entries, and you have like 30 here. So like technically you can just generate like all 240 cases and just copy the answers in. We're not gonna do that. We're gonna find a way to solve this ethically. But I guess like now that I know that bound is like quite large, like look at this one here. We have to like think about what the time complexity should be for these type of questions. So I guess like one thing I noticed is that like we are dealing with palindromes, right? For both sides here. So whenever we are dealing with palindromes, we are actually like let's say our number is like 1 billion, right? If we only have to check every palindrome, we actually only have to look at like the square root of the largest number, because like a palindrome is like basically you cut the number in half, right? And you only have to like check one end and not the other end. Let's see, the acceptance rate is like not too low, so yeah, so that's like the first idea I have. So like for example, for this case here, let's say so I guess like we also need a quick way to like turn our numbers into like the base k, but we can do that like in, I think, like log k time, if I'm not wrong. Yeah, but let's just look at the first example. So what I'm saying is like we can start off with like all the palindromes for base 10, because like remember we are summing these numbers, right? So even if we have to like generate, I don't know, a palindrome of like 10 billion big, well, we only have to like, well, if it is like a billion, it would be like 10k numbers, right? Well, technically it would be a bit more than that, I think. Yeah, but like if it is 10 million, well, it would be like roughly 30k. I think like with all the all the cases down there, like you have like 4 numbers here, 1 in the middle, and then 4 there. Like counting all those cases, maybe I don't think we'll actually reach like 150k to 200k amount of palindromes. But yeah, this is like the absolute upper bound. I don't think it will go through that. So based on that, we can actually just generate all the palindromes on the base 10 side, and then for each of them, we can use log n time to check the different bases. And then that should give us the answer at the end. In like a quick enough time. So now we have to think about how we want to generate all the palindromes. Well, turning into base is very simple. We just like I'll show it when I'm coding. But yeah, we still have to think about how we want to generate the the palindromes. So we have like an odd number of um digits on base 10. Well, like you have the single digit ones, but you can also have like, like one digit in the middle, um, and then you have like two. Well, you have like two mirror sides here, right? Or if it is an even number of digit, you have like two sides, and like this side is like the mirror of that side, right? Um, yeah, so we have to like think of ways to like gradually generate them. So I guess like what we want to do is like, because we kind of leading zeros, right? We want to generate on the left side. So, well, like when we are dealing with odd, our middle, um, well, it could be like 0 to 9. Let's say we have like more digits here to make it like a more generic case. Um, so on this side, we can start with 1 0 0, like a lot of zeros, right? And then like the middle number, um, we can have like 0. Yeah, so we should update the middle number first, and then like we keep going, right? We don't really care about this end here. Like we only need that when we are actually forming the number. Um, yeah, so we have like 1 0 0 all the way up to, well, and then like technically you have like 0 to 9 here as well. And then you want to like update this, and then you want to like repeat, update this, and then repeat. So actually now that we kind of thought about that, um, if we look at this side here, well, we're basically just like going from like 1 0 0 0 all the way to all nines, right? So we can just make a loop here. Um, yeah. So that's for the odd case. For the even case, I think yeah, again we have like 1 0, a lot of zeros, and that's just the mirrored side. Um, and then we have like 1 0 1, like all the way up to like all nines. So again, we can just do a loop here on the left side, and then like we kind of like pad the right side there, if that kind of makes sense. Yeah, but that's how we would generate the palindromes. I'm thinking of using like turning them into a string and then reverse it and then like pad them together. I hope that's fast enough for our purpose. I think it should be fast enough. Yeah, like you can think about this as like an n log n solution where n is like well, like the maximum amount of palindromes we have like within like 40 billion is like 200k. Let's say 200k. And then like converting this will just be like log n. So yeah, let's just code it out until we get timed out. And yep. So first thing we want to do is we need a function so to base k. Yeah, so I can show how I would like how I would turn a base 10 number into base k here. So what do we have here? Just I guess like we can just check whether base k is palindrome. So is base k mirror. We can just do that. So boolean. So I think what we want to do is we have like base k here, which is a list, and then what we can do is while x is greater than 0. I think we just keep wanting the we just keep getting the last digit. So what we can do is we can just do base k append x modulo k, and then we get rid of the last digit. So we can just do divided something like this. Yeah, so maybe I'll draw up the base 2 kind of example, and that will kind of explain how that works. So let's say we have like 101, right? So what we want to do is so this is like 5. When we modulo 2, we are basically checking whether this is a 0 or 1. So it'll be like on the result thing, we'll have a 1 here, and then when we divide this by 2, we're basically doing a shift in the a shift to the right by 1 in the base 2 case. So like it'll shift that way, like, and then we'll have like 1 0 here, right? And then like, yeah, and then we can like get the modulo, so we'll get 0 here, and then we'll shift it like 1 by right again, and then like modulo, we shift that, like it would be 0, so we just end it off there. And then for this case, like actually like we're getting the digits like from right to left, right? So like technically we have to reverse it to get the correct thing, but we don't really care here. We just want to see if it is mirror. So we want to see if we are like, after we reverse this, do we get the same number or not? And we can just use 2 pointers for this. So yeah, so we have LR length of base k minus 1. So now while L is smaller than R, if they're equal, they're on the same thing, so it doesn't matter. So while this if base KL is not equal to base KR, we can just return false. Otherwise we'll move the left pointer 1 to the right and right pointer 1 to the left. And then if it passes this, we can return true here. So now we have a function to check is base case, like is the base k is base k mirror in this case. So yeah, we can start generating all the palindromes. So what do we want to do here? We want to start with so we should start with like is odd. So at the start we are doing odd. So I guess like we should also have the number of digits. So we set it as 1 here. Wait, actually number of digits, we can just do it in a loop, right? So we have like digits 1, and then like at the end of the loop we can just add 1 to like our number of digits, and that will actually allow us to keep track of, well, whether we are in the odd case or in the even case. So so if digits modulo 2, so that would be if like we are in the odd case, because like this is equal to 1, right? And then like this would be like modulo like this would be like divided by 2. So I think like this case might be a bit they should be pretty much the same. So we just need to write a loop for I in range. How do we want to do this? So we want to go from, I think like so we need the correct amount of digits. So let's say we have 3 digits now. Yeah, let's do the even case first. Even case is a bit easier. For I in range, so you just have to divide this by 2, and that's the amount of digits we want to work with, right? So for example, if we have 4 digits, we have like 2 digits on the left side. So if we want 2 digits, how do we actually get this like in the correct manner? I think I know how to do it. So we can do 10 to the power of this minus 1. So that should give us, yeah, so let's say we have like 4 digits here. It will be like 2 here and then -1. So we will start from like 10 and then we have to like go all the way up to 99, right? So so in this case, we can just do digits divided by 2. So if it is 6 here, yeah, so if we have 6 digits, we have like 3 on the left-hand side, and then -1, we will get like 100, and then this should give us 1,000, but like we only want to go up to 99. Okay, so that's the even case. The odd case, I think it will be something similar as well. Oh, oops. I recently realized that highlighting on a trackpad is actually like very inefficient, like compared to a mouse. But yeah, okay, let's get back into this. So let's say we have like 3 digits here. If we have 3 digits, we want to look at 2 digits, right? So after we divide this, I guess we can just do like digits plus 1 divided by 2. I think that'll work. And then like obviously you just want to get up to that there. So if we have like 3 digits, we want to look at 2 digits, right? So we'll have like we'll have 10 here and we'll have 100 here. Yeah, okay, that should work. And then like whatever is inside should be very similar, but again we'll do the even case first, because that one is just a lot easier to deal with. So what we want to do is we want the actual number. So the actual number should be I guess the actual number should be an int. So we turn I into a string, and then plus also I into a string, but then we have to reverse this string. I'm a bit worried that reverse list will be quite slow. Should be fine though. Let's just do that. So we reverse the string and then we have to like turn it back. Oh, we can't just turn it back into a string. We have to do join like this. Yep. So reversed and then join. Yeah, so that should give us the int we are looking for. And now we just need to check if is base k mirror for our base 10 number. If it is, then we can add it to our final result, right? So I guess we should also keep track of like num found. So we can just do res. We add num in there, and then what else can we do? Yeah, we have to like add that to num found. And then I guess like yeah, if num found is equal to n, which is the number of like these k mirror numbers that we want to find, we can just return res here. Yep. Otherwise we just keep looping through, I think. Yeah, otherwise we just keep looping through and like we don't really have to do anything. So let's just copy this here, but then for this case we actually want to get rid of the last character, because like let's say for our odd number we have like 100, right? And this is the middle number, right? But like currently we have this. So if we make this a string again, we want to get rid of this and then like flip it around, right? Like and like put it here, because like we don't want like 2 of the same duplicate in the middle. So that's why we need the -1 here. So it's base case, base k mirror. Yeah, if that's true, and just add 1, and at the end we can just return res. I'm not sure if this works. I give it like a 70% chance of working. Base k. Oops. Oh, okay. That's cool. That's cool. And it works. Nice. Nice, nice, nice. Um yeah, I guess I should be a bit more like confident in myself. I do want to see how people do it. Yeah, see, like this is what I'm talking about. Like you can just cheat like this. Like just get all the answers and then like because you only have like 240 amount of different test cases. So you can just do that. Um yeah, but let us kind of like go back to this. Um yeah, I think this question is I will admit that I have seen something a bit similar before that I kind of like took advantage of. And that would be like the the palindrome thing being like squared, like being the square root of n, like kind of concept. But yeah, let me. I can like talk about my whole like how I got to my solution like now. So and I'll talk about like my palindrome thing as well. I think is like that appeared in like some other. It's not exactly this question, but like I saw that technique like in another like hard daily question. Um, so I guess like the first thing you have to do. I did cheat a tiny bit to see what the largest number we can get to. Um, but I think like because I guess you can like kind of prove like how large it can go into, but I'm not that bothered. But like the first thing you have to know is the largest number is like 43 billion. And that's like when we sum up all 30 numbers, right? So like on paper the actual largest number would be like even smaller than this. So that's the first observation, right? Um But like obviously you can't just test like all those like 10 billion. Let's say 10 billion. Let's say 10 billion. We can't just test all these 10 billion numbers, right? Um but if you think about it in the palindrome way, actually we can. We can test all the palindromes um inside like these 10 billion numbers. Well, why is that? Um because I I propose that we only have square root of 10, like around square root of 10 billion palindromes in like from 1 to 10 billion. So if you think about the even case, well, if you have a 10 digit number, that has to be a palindrome. Yeah, missing one. Well, that means the left side determines what the right side have, right? Well, how many digits do we have on the left side? Well, only like half of like the 10 digits, right? So we only have to like deal with 5 of these digits. So like, well, of course these could be like anything, right? It could be anything 5 digits. But it also means that like instead of having to test out all like all 10 digits of like I don't know, like from this to like to that, instead of having to test out like all of these 10 digit numbers, we only have to test out all these 5 digit numbers. And then the odd case is like a bit more because like so let's say we have like 9 numbers, right? 9 digits. We actually have a middle number, but again, whatever we have on the left side plus the middle number determines what we are going to have on the right side. So if we have like 74231 here, well, it determines that like this side has to be 3247, right? So again, we only have to check a bit more than half the number of digits, and that translates to square root kind of um a square root kind of relationship. And yeah, I think like after you see this, and if you cheat it like me and see what the largest number is, it's quite obvious that you can just check like the square root of this number amount of palindromes. So I forgot what the square root of this is, but like I think like counting the odd number cases, like where you have a bit more, the upper bound should be like maybe like 150k amount of palindromes within here. I'm pretty sure the square root is like way less. It might be like 30k. But like after we get this number, we also have to think about how much time it takes to actually check its its base k form, because we want the base k form to be a palindrome as well, right? Well, this is where this code comes in. So this code here, I can move it down a bit. Yeah, this code here. Oops. Yeah. So basically, like I think I've explained it during my well, like when I cooked this out, I kind of explained it. But I can reiterate that. So let's say we have a 5. So this is base 10. And then we have a base 2 here. So what I'm doing here is I'm getting the modulo of base k. So let's say like k is 2 here, right? Oh, I actually forgot to show this thing at all. But yeah, yeah, I can like talk about this. So what I said before is if you have 10 billion numbers and you only have to look at the palindromes, it will be like the square root of that, because like an even number you only have to like check the left side, so like half the digits. For odd number you have to check like a bit more than half the digits. So like that's where the square root comes from. So let's look at this case now. I forgot that I need to click on the thing again. So that was kind of my bad. So if we take the modulo, like if we take like 5 modulo 2, what are we actually getting? We're getting the last digit here, right? So like we'll get 1. So we'll get 1. And then if you look at the code here, I'm doing like x divided by k, but like in the integer sense, right? Actually, like what this does is it shifts right in our base case. So in this case, it will be a base 2. Yeah. Is this like something that's a bit hard to wrap around? Let me think. Yeah, okay, let's do the base 3 as well. So let's say we have like 1, 2, 1. So what was that in base 10? Base 10. That will be 1 plus 6 plus 9, which is 16. So like I hope I convinced you that like if you do modulo, you do get the last digit, right? So now we want to like do a right shift so that the second digit becomes the last digit, right? So what happens if we divide this by 3? Well, when we divide this by 3, you kind of like only keep this thing, right? Because this is the remainder. But then when we do like the Python divide, like this integer divide here, we don't keep the remainder. So we'll only get our like we'll only get our like the stuff that we want here, and we get rid of the remainder of 1 there. So yeah, this is like kind of the idea. And like because we like every time like we keep dividing it by base k, our number like exponentially gets smaller like every time we divide it, right? So this is like where the log k comes from. And yeah, and the rest is like checking the digits, so that shouldn't be like too big as well. Like we have like log k amount of operations here, meaning that we have log k amount of digits here. So again, this is going to be a log k operation because we have log k amount of digits. So yeah, so this whole thing is log k. We have around like what 150k um, possible palindromes here, maximum. So it'll be like an n log k, and that's obviously fast enough. So that's kind of like how I thought about the idea. The code uh, is it takes a bit of brain power to like think about like how to turn the number of digits into like the range we want, but other than that, it should be like pretty much fine. So yeah, um, I think this is a very interesting question, and like it reiterates like the number of palindromes being like the square root of the upper bound you want to go to, and yeah, I think it's a pretty good question, and yeah, please leave a like if I help you in any way in this video. It really helps out the channel, and if you can or if you want to like give me a subscribe as well, like that would be very helpful. And yeah, thanks for watching, and I'll see you tomorrow. Bye.